I'm going to walk through these steps, then I write it on the board. I will start with, let's write the steps together. So I'm going to write something like, maybe I just pick a question. This question says, prove that 11 to the power n, no, don't write, just listen. 11 to the power n minus 6. Yeah. Minus 6 is a multiple of 5, or is divisible by 5. Is divisible by 5. Prove that, for all n belonging to n, that is for all natural numbers n, 11 to the power n minus 6 divisible by 5. So please listen. Leo, I didn't ask you to work on the calculator, I asked you to listen. I took this mistakenly yesterday. I brought it back. So the vampire doesn't come looking for me. Anyway, the first thing we will do in inductive process, to induce, can somebody check what the word induce means? Induce. So this thing, sometimes when you understand the English, the grammar, then it makes it easier for us to connect to the idea. All right? Induce. Hard. Yeah, me too. The moment an African tell you it's feeling hard, then it's really hard, right?
It's feeling hard, actually.
Yeah, it's really hard.
No.
So.
Induce or induce?
Induce. What does that tell you? Quickly, please. Can you stop and be focused? You need to learn to know when to stop talking. Seriously. I know we like to have jokes. I like to have jokes, but you need to know when to stop. Yes, miss.
Succeed in persuading or influencing someone to do something.
Okay, can we check what that meaning?
Bring about or give rise to.
If you put that on, there should be this by default Google definition. You have like 2 or 3.
Just induce.
Just induce. Just the word induce. The verb.
Produce.
Produce. What is she looking at?
Definition. Bring about or give rise to.
Yeah, bring about or give rise to.
I said that.
She said that? Oh, I didn't hear that, sorry. Okay, listen. Give rise to. So to induce means to give rise to. Please listen. So when you're proving by induction, you're trying to tell us this process give rise to this conclusion, basically. Do you understand what I mean? You are working through a process. Oh, based on what I've done so far, my conclusion, the entire process give rise to this, leads to that, something like that. I can conclude from this. But you must have done some logical processes. The first thing we try to do is to label. I will encourage you to label your statement. The statement is, this is the statement. Or even from here. Or maybe this. This is not supposed to be included. We can label this statement as Pn. So Pn stands for 11 to the power n minus 6 is divisible by 5. So which means P1 will be what? 11 to the power 1 minus 6. Do you understand that? So Pk will be when n is equal to k. So the first thing I will encourage you to do is let Pn be the statement. The next step in an inductive process is to check for P1 at least. When I was learning this, my lecturer, Mr. Shojabi by name, will insist that we check for P1 and P2. But P1 is sufficient, okay? But you can do P2. Sometimes when I'm doing it, I will check for P1 and P2, but P1 is enough, all right? You check for P1. Does it make sense by P1? Okay? Does it make sense by P2? So, I would say the next step is check. Remember, this is a statement, okay? Check if P1 and P2 are true. Like I said, when you're working, P1 is sufficient, but I'm going to just work with P1 and P2, all right? After we check that these two are okay, then we assume that Pk, which means the statement at K, is also true. We have checked for 1, we have checked for 2, then we will assume, oh, suppose pk is true. Now k could be anything. K could be 1,000, k could be 10 million, k could be 3. Do you understand that? Suppose pk is true. That's the next one. We call that the inductive hypothesis. You remember what hypothesis is from yesterday? What do we say hypothesis is?
Assumption.
An assumption. Okay? We are now going to assume that pk is true. That is why we call it an inductive hypothesis. So, assume, now state your inductive, from the word induction, hypothesis. What does that, what do I mean by that? It is, assume that pk is true. Okay? The next step is to use step 3 to prove that pk plus 1 is true. And the final step is just to conclude. Conclude that Pn is true for all n in n. What is this set?
Natural numbers.
Natural numbers. I'll go through this again. First step, Karen, I need your attention. Let Pn be the statement, which is what exactly is the question talking about. In this case, my Pn will be 11 to the power n minus 6 is divisible by 5. Okay? The next thing is check if P1 and P2 are true. You do the basic ones. But the fact that P1 and P2 are true, or even P3, even if you check up to P10, doesn't mean everything is true. Do you understand that? Let me see how I can justify that. There was a class I was having, and we were, okay, let's see, 2 raised to the power 0 is 1, 2 raised to the power 1 is 2, 2 raised to the power 2 is 4. So 2 to the power n will work, because I have these 3. Also, is there other way I could get this 143 without power of 2? 1, 2, 4. Is there another way? Okay. What? No. Okay. Maybe I stop at the first 2. I write this. Somebody claimed that all you have to do is 2n to get it, where n begins with, or let's say 2n minus 1. 2n minus 1 to get this. Does this work for that? No, okay, that's not what I wanted to get. Or 2n minus 1? Is it? What exactly is the problem, please? What is the problem? I expect you to think and not laugh. 2 things can generate this for us.
Would just be n.
N. Okay. Oh, okay. That's a simple way. I'm trying to get 2 different things that work for it. One is n. One is 2 to the power n minus 1. Do you agree? If n is 1, you get 1. If n is 2, you get 2. Right? And also, if n is 1 here, you get 1. If n is 2, you get that. Right? Do you know the next step? But for the first 2, these 2 are valid, right? So if someone claimed that the n term of this sequence, after checking this, definitely, then this is the n term. Are you sure when you get to the 3rd step, this still works? Because at the 3rd step, both of them will be different. Why this will produce 3, this will produce what? So my point is, the fact that it works for the first 2 doesn't mean it's always going to be like that. I'm trying to think of there was a sequence we were doing in the class with maybe Form 3 last year. That was the one I thought I could remember. It was so convincing, inspecting the first 5 terms, and somebody wrote an end term. But that wasn't the original end term. But by guessing, the first maybe 3, I think, the first 3 works for it. And the person just imagined 1, 2, 3 and just wrote the conclusion. But if you look at the 4th, it doesn't satisfy it. Do you understand? So there was I think it was a quadratic sequence that somebody mistakenly just, oh, I don't need to go through the long process of inspecting and wrote something else. That's the point I'm trying to make. So the fact that it works for the first 2 doesn't mean it will always work. That's the point. And as you can see, it depends on the next term. Both of them don't work for it. So you have to be specific. If you are dealing with this, you know the next term will be 3, 4, 5. If you are dealing with this, it's a different thing. But for the first 2, don't assume, oh, maybe this and this are going to be always the same. No, they are not. Okay? So that is why the fact that we check P1 and P2 doesn't mean, oh, we can actually conclude that, yeah, this is true. No. It could fail at some time somewhere. But the next 2 steps will justify whether or not it's true. The next step is to assume. Now, if you are able to, this is the process. Okay, this is the process. You start from 1, you start from 2, and you conclude. Now, if you are able to assume that at this point, you can always conclude for this point, then you are okay. Because this point could be anywhere. If I assume for this point, and I can use that to justify that the next one is true. So each time Karen is accurate, Lillian will be. Or I say each time someone is accurate, the next person will always be also accurate. Then that someone could be anywhere. If I begin from Krista, what does that tell me? He must also be accurate. If I begin from you, then Leo must also be accurate. So because we are able to justify that if a term is true, the next one is also true, then it means we have concluded for everybody. All I need to do is start from 3, then 4 is correct, right? Now that 4 is correct, what does that imply? 5 is true. If 5 is true, what does that mean? 6 is true. Now, does this sequence terminate to you? Is there a point where something is true and something is not true by that generalization? No. No, because you have generalized already. Because you pick K arbitrarily. Okay? You pick K. You never said, let's suppose that 100 is true. The fact that 100 is true and you're able to prove 101 doesn't mean 102 actually is true. But because K could be anything. So this is the inductive process. Okay? Or the process of proving by induction. Maybe we begin with this one. Let's see how it works. You may write if you want to. So we're going to begin with this one. Let's make sure we have everything covered. We'll begin with the question I just wrote. Examples. I'll take one, then maybe the next one we'll do together. Okay, prove that instead of writing for all natural numbers n, I will always write like that. This means for all, just like you raise a to power -1, basically. Come on. It's a language, you speak like that, it's allowed. It's legal for now. You might see this as this. Means the same thing for someone studying maths later. And when we write this for you, this is how you see it. 5 divides this. This means divides. Okay? So when you say 2 divides 10, it means 10 is divisible by 2. So that's the difference. It's the same thing. Are you lost? Because there's no food? This is what I'm saying. Look,
You
it's
should
not
bring African chicken to our class.
Right. 2 divides 8. Do you agree? 8 is divisible by 2. They mean the same thing, right? So using the symbol, 2 divides 8 is this. Okay? 8 is divisible by 2 means when 8 is divided by 2, there's no remainder. So it's a way of writing it if you want to put it the other way around. Okay. So instead of writing this, you might be seeing that in future. Anyway, so please, can we all look at the board? Everybody, let's look at the board. So again, the statement will be, let p to power n be the statement. You don't have to repeat it. And this is the statement. Or this. Okay? Let p to power n be the statement. So, you check for p1. In the case of p1, I have 11 to power n, 11 to power 1 minus 6, which is what? 5. Is it divisible by 5? Or you don't even have to write the story. What does it mean to say something is divisible by something? I want you to think in general now. If I claim that A is divisible, do we get this part? A is divisible by B. What does that mean?
There's no remainder.
There's no remainder what? When what? You can't just say there's no remainder. Well, yeah, that is an incomplete statement. When B is divided by A. Just put a number. A is divisible, are you sure? A is divisible by B. So which one is greater?
A is greater.
A is greater. So put this as 10 and put this as 2. Now, think again.
When A is divided by B,
There's no remainder. Or there's another way. What?
Factor.
2 is a factor of A. Or good.
B is factor of A.
No. Multiple. That's the best way to represent it. So 2 is divisible by A because you can actually write 10 as some multiple of 2. Do you agree? Does that make sense? Because this is the idea we need here. If 10 is divisible by 2, it means 10 can be written as a product of 2 and another number. And that number has to be an integer itself, negative or positive, nobody cares. Okay? So when we say A is divisible by B, it means A can be written as some k times B, where k is an integer. So that is the idea. How do we know this is divisible by 5? Because 5 itself can be written as 5 times 1. Is this one an integer? Yes. Then this shows that P1 is true. If you check for P2, 11 squared minus 6. 121 minus 6 is what? 115. Can we write that as 5 bracket something? What is that?
23.
23. So indeed, it's divisible by 5. Once you can factor 5 out, it's divisible, 5 can divide it. That's the idea you need to look into. So the conclusion for this step is that so P1 is true. Instead of writing the statement all over again, we just use P1 is true. And here it means, or you can just say, this implies that is this line implies that. Can you see we are using all these statements of implies and all that? This implies that P2 is true. You don't have to use so. You can. It's more. How do I say it now? It's a more technical term than just using so and all those kind of stuff. Okay. So we are done with this step. We have checked and we have seen that P1 and P2 are both true. Okay? The next step is to now state our inductive hypothesis by saying, suppose that Pk is true. Okay? Now what does that mean? It means 11 to the power k minus 6 equals what? Can somebody guess? 5. Of course. Because we have k already. Okay? 5 what? A. I'll take m for math. That's good. You can use any integer. Okay? So this is, suppose that pk is true. This is what it means. It means when n is equal to k, you can write it, you can factor 5 out, and this will be an integer. Then you say where m belongs to n. Let's put it that way. Or belongs to z, because it could be positive or negative. Does that make sense? Any question? Not n here. We need it to be an integer. We don't need to be a natural number. There's a difference, right? Because natural number is restricted to positive whole numbers only, or positive integers only. Okay? And it's possible when you do the power and subtraction, what if you get something like a negative? Which is not the case in this, because there are some questions you can have that. And 5 can still divide them, even if it's a negative integer. Do you understand that? So, this is our inductive hypothesis. Now, we use that to prove pk plus 1. You don't need to write that. I'm just trying to explain what we are doing next. So your pk plus 1 means what? 11k plus 1 minus 6, isn't it? We need to be able to get to the point where we get what? 5 and some, maybe p. Where p is an integer. Do you understand? We need to get that. There is something about induction, proved by induction. Your inductive hypothesis has to be used here. If you get some corner method, shortcut, that's what I mean by corner where I come from. corner. You get some shortcut, and it does not involve your pk, you have not proved by induction. Because what is the idea of induction? If I can assume that she's telling the truth, and that assumption can justify that the next person is telling the truth, and that shows that everybody is telling the truth by default. Do you understand that? Any arbitrary method, any arbitrary step that I pick, I can justify that the next step is true. So you are actually basing your justification on the previous one. It has to be used. So we need to now think about how to do this. Is there something we can do to this? Is there something we can do to this? It doesn't look like difference of 2 squared to factorize and all those things. Yes, what do you
make it 11 to the power of k times 11.
Good. So we can make it 11 to the power of k times 11 minus 6, right? Right? Or we could write that as 11 bracket 11 to the power k, then minus 6, isn't it? Now think, how do you think we could use this here? How do you think we could use it here? Because remember, the instructions say, use this to prove that. 50. Substitute what? 11 to the power k. Good. But we don't have 11 to the power k. Yes, no, you have said the right thing. But we don't have 11 to the power k there. What do we do?
Oh.
Yes.
Turn that 11k minus 6 equals 5 and 2 to the power of k equals 5 plus 6.
That's it. So from here, make 11 to the power k the subject and substitute here. So which means, from our inductive hypothesis, from 11 to the power k minus 6 equals 5m, it implies that 11 to the power k, can we see this?
Yes.
Equals 5m plus 6. Does it make sense? Maybe I'll use this part now, so I don't go to, we don't want to stress the Japanese scale. Hello, Japanese scale. So, which means this implies that p to the power k plus 1, or let's say p to the power k plus 1 now becomes, you can see I'm not saying equals to. Okay? It's not an equation. I'm just trying to say, okay, I'm now back to p to the power pk plus 1. Okay? pk plus 1, where did we stop? We stopped at 11 to the power k minus 6. This was where we stopped. We had to, look for something. Now we want to continue. So you need to be logical about what you do. I need to be organized with your proofs. Okay? This can now become what? 11, yes? 5m plus 6 minus 6. What do we do now? Expand. 55m plus 66 minus 6. 55m plus 60. Yes?
Why can't we use equal?
Equal is that?
No, not like for the.
You mean this one?
Yeah.
No, I'm just saying, this statement, the statement here is P1. It's just something to identify that step. Instead of saying P1 is, or the statement P1 becomes something like that, it's not an equation. This is the expression we are trying to solve. Okay? This is not so significant, but it's not just, I don't know how to put it. It's not just ideal to me to say, oh, P, because I said, let the statement P be, okay, maybe if you use it sometime, maybe it doesn't really matter. But if I use P, K plus 1 equals, I'm trying to tell you that Pk plus 1 is maybe 5 times something. I'm trying to say that this is my statement. I want it to be a statement, not something of algebra, equation, or something like that. I don't know if you get what I'm saying. I'll think for maybe one more way to answer your question. Yes, quickly. What is our goal here? To factorize what? Is it possible to do that now? Yes. So 5, 11m plus 12. Can we now say that pk plus 1 is true? Is it? Because how do you know that this is an integer? How do you know that this bracket gives an integer?
M is an integer and there's no fractions.
So there's no fraction. No. Yes, of course, m, everybody's right. Since m is an integer, 11m is an integer. An integer times integer gives an integer, right? Now an integer plus integer gives an integer. So the bracket is an integer. Because you have to be sure of what you're saying, not just because m. What if m is an integer and the bracket still is not an integer? You have to convince us why. Okay? So this is divisible by 5. Should I say this is this? And since 11m plus 12 is an integer, okay, then pk plus 1 is true. Can you see? This is like a statement. So that's why I'm not so comfortable with using equal to, something like that. Because if I say that, what I'm saying is that if I equate it, then this is my pk plus 1, right? Then I'm trying to tell you that 5 into bracket this is true. That doesn't really make sense. Do you understand? So that's why I don't use equals to. But it's not so important, yeah, particularly at this level. Does this make sense, everybody? Now you can see we have used the pk to prove that pk plus 1 is also true. Assuming pk is true, pk plus, so which means assuming 99th 1 is true, step is true, 100 step will be true. Assuming 1 million step is true, 1 million and 1 step will be true. So which means for any position you pick in natural number, the next one is also true. That means it's true for all natural numbers. Because for every natural number you pick, there's always something up in front of it, right? For every natural number, there's another number right above it. Does that make sense now? And if you continue like that, you've covered all the natural numbers. Of course, you can't count all the natural numbers anyway. Do you get the idea? So that is the step we have just said. We have proved that pk plus 1 is true. Now your conclusion. Therefore, maybe I just continue using my purple.